thank you very much for the opportunity to speak here. We all know that sustainability is a very important topic. We're constantly thinking about sustainability of species, sustainability of our environment, sustainability of the human population. I think of sustainability together with another term, collapse, because we have collapses going on all around us all the time, and part of the whole evolution of our society, of our culture, and of our species and like is really built on a combination of some things running very smoothly and moving into the future and other things collapsing. So I'm going to talk about sustainability both from an environmental standpoint but also in a broader standpoint of sustainability and collapse in a wider variety of venues. I'd like to ask a question of the people in the audience here. How many people in the audience would feel comfortable telling me what the figure is that's shown on the first slide? I see a couple of tentative hands, not really an overwhelming confidence that you know really what the slide is. And if I made the question more specific and said, what is the name, not the species, but the actual name of the bird on that slide, I bet there's probably only one or two people that would know the answer. I see a couple of heads nodding. That bird is named Martha. That is the famous last passenger pigeon. And I'm very glad to have a chance to talk to you today, and I'm very glad that you're here because we should all know about Martha because of the lessons that that story really gives us about our own future. A few centuries ago, the most populous bird on Earth was the passenger pigeon. They inhabited the eastern part of the United States. They spent the winters in the southern United States, and they then moved north to breed in Michigan, in Pennsylvania, in upstate New York, and in southern Canada. And when these birds traveled around, they traveled together in flocks that might number 100 million or even 1 billion birds. The skies were said to turn dark when a flock of passenger pigeons passed over, and it might take a whole day for a flock to pass. You don't see flocks of birds like that anywhere today. What is really amazing to me is that we obliterated them. We completely eliminated the passenger pigeon. I can understand how we could eliminate the rhinoceros, the elephant, some species that are certainly in danger these days, because they have a limited space to move in, and they have limited numbers. But 1 billion birds can't escape from people trying to hunt them down, for example. It's really an amazing story, and we'll come back to it a little bit later on. But before we do that, let me just say that I've been working in the environmental business for a long time, not only in academia, but in the consulting world. And a lot of people say, what's a mathematician doing working in the environmental sphere? And I say mathematics is the field that you use when you want to understand the quantitative relationships between things, like the decrease in the population of a species, the collapse of a stock market, a collapse of some kind of a plant, like the plant in Japan. You're interested in trying to understand quantitatively how much risk there is to different kinds of things, and how you might head off collapses of such things in the future. Almost every environmental question, at least, is a quantitative question. What is the risk to this? What is the impact of a change in CO2 levels to the global temperature? What is the effect of a change in pesticide use to the population of different species? All these questions are quantitative questions, and I use mathematics to try to put a quantitative framework on these kinds of questions and make some headway in really trying to answer them. The work I do is very interdisciplinary. It's using mathematics to bring together many different other fields. Economics, biology, chemistry, physics, meteorology. Many different areas come together, but the unifying theme is really the mathematics. And when I look at sustainability and collapse, I see 6 different phenomena, 6 different kinds of dynamics that are fundamental to understanding collapse, understanding sustainability issues, and really quite different from each other. Let me give you a brief rundown. As you can see on the slide, the first one is low probability events. You all know that you've probably heard that the dinosaurs were most likely done in by a low probability event, the crash of an asteroid off the Yucatan Peninsula of Mexico that created so much dust and the like that it changed the Earth's climate, and the dinosaurs were unable to adapt to the change. You are aware of the Japanese Fukushima nuclear disaster. Low probability event again. You had an undersea earthquake, led to a giant tidal wave, wiped out the plant, wiped out a lot of the coastline of Japan, wreaked havoc in so many ways, and we didn't anticipate it, or at least the Japanese plant operator did not anticipate it. We don't do a good job of estimating low probability events. We could do a much better job of doing that, and there are mathematical methods that would let us do that. A number of years ago, I was asked by the Environmental Protection Agency to carry out a quantitative risk analysis of the idea of burying radioactive waste in abandoned salt mines in different parts of the country. And one of the areas of the country that was considered was along the Gulf Coast, because there are lots of salt mines along the Gulf Coast. And one of the things that we were concerned about was the risk that somebody in the future would drill into one of these salt mines that had the radioactive waste in them and release the radioactive waste to the environment. So to try to understand that and to try to quantify the probability of that, so 1 in a million, 1 in a billion, 1 in 1,000, what is the probability of that? I went down with some of my colleagues and we took a helicopter out to the Gulf Coast, and we landed on some drilling rigs and some production platforms and talked to the operators down there about, is there any risk when you're drilling? Do you know where you're drilling into? Do you know is there any risk, any chance at all that you could go into some underground salt mine? They said, absolutely no. Probability is 0. It's impossible. We know exactly where we're going. We also went down into some salt mines along the Gulf Coast, and the people, we said to them, do you worry about those drill rigs that are up in the Gulf of Mexico? Do you worry that one of their drills might be going sideways or something and come down into your salt mine? Not at all. Not at all. They know where we are. We know where they are. No problem. And then I think it was November 1980, a Texaco drill rig put a large hole, I think about a 12-inch diameter hole, right down into an operating diamond crystal salt mine on Jefferson Island in Louisiana, and changed the whole way people looked at the risk from events of that type. In fact, it was so disastrous that the drill rig, which was on a barge, and about half a dozen other barges disappeared as an entire lake went flying down through this enlarging hole into the salt mine to be buried. They've never been seen since. These components, and they're somewhere in the earth between the surface and the old salt mine. The people in the salt mine went running out the other end, up the shaft as fast as they could. Nobody lost their lives, but we learned a big lesson. We don't do a good job estimating low probability events. But we have methods that could help us do a better job. We have mathematical methods for doing some kinds of things like that. Group behavior is another interesting phenomenon that can lead to collapse type issues, either in the environmental sphere or in other spheres. In the environmental sphere, the passenger pigeon, like many birds, used to fly around in flocks. You see a lot of birds that do fly around in flocks. They group together. They look for food together. They protect each other from predators. They mate sometimes only when they're in larger groups. So some kinds of group behavior is natural to certain kinds of species, and to humans. Lots of humans follow the same investment patterns in the stock market. When everybody follows the same investment patterns, that can actually cut down on the returns and can lead to greater risk. Because if everybody changes their mind at a certain point, then things can crash. Group behavior can cause a lot of problems. For the passenger pigeon, the fact that they flew around in groups made it really easy for people to hunt them. Because this big flock would come in, they even loaded shotgun pellets into cannons and shot them into these flocks of passenger pigeons, had them go down by the hundreds. And then they convinced, they used to kill the passenger pigeons for food for animals, but then some smart marketing person decided, let's try to convince the people in New York that passenger pigeons are a delicacy to eat. And it worked. All of a sudden, all the greatest New York restaurants wanted boxcar loads of passenger pigeons to feed to their patrons. Group behavior again. So group behavior is an interesting dynamic, and it's something that we can also model mathematically. Games and evolution, the third lens through which I like to look at collapse. We live in an environment where we compete and cooperate with each other. Companies buy things from each other, but they also compete with each other. Species interact with each other in cooperative ways, but then they also compete with each other. What really happens is that as different entities compete with each other, they evolve and gradually change their characteristics, take advantage of their environment. What people don't often pay as much attention to is not only does the individual species evolve, because that's usually kind of slow, but the whole ecosystem evolves. And the ecosystem evolves a lot faster than the individuals in it. Usually the individuals in it die off as the ecosystem kind of changes, and other groups of species come in and replace them. So the evolution of ecosystems is something that we can often model effectively mathematically, and it's something that's really key to issues of sustainability and collapse. Then we come to this topic of instability. Now, instability is a really, it's all over the place, but does anybody in the audience have a book that I could borrow for a second? Thank you. Watch this experiment for a second, if you will. I'm going to take this book, I'm going to spin it. It stayed kind of in its trajectory as I spun it around. Do the same thing going the other way, except for the cover flapping. It flips just fine. But now watch this next one. I'm going to go on the third axis of symmetry, this one here. You think it's going to flip fine, right? Well, it doesn't do it. Look at it carefully now. It won't even stay anywhere near the trajectory that I put it on when I flip it, because that's an unstable mode of motion for this thing. And we have to be very careful about things becoming unstable, because when something is unstable, like the book, it flies off its trajectory very, very quickly, and the motion here really essentially disintegrated and collapsed. So instability is something that can lead to gross changes in the environment and the like. Nonlinearity, sometimes you think that the future is going to be the same way it's been, things have been in the past. You think that if you always got 5% interest on your bank account, that you're going to get 5% interest on your bank account going into the future. Now, we've all been disabused of that philosophy. Now we don't get any interest on the future. But I spent many years just assuming I could get 5% interest on my bank account. I made a linear assumption that the future would continue along the same line that it was in the past, and it was wrong. And there are many spectacular cases of nonlinearities, of deviations from that linear assumption that have caused things to really collapse. And we need to understand those things. When you think about weather forecasting and how hard it is to predict the weather, how hard it is to understand where a hurricane is going to hit the Gulf Coast, even a couple of days before it gets there, you're dealing with nonlinear effects, very unpredictable kinds of effects. And my last category that's also amenable to mathematical analysis is network effects. You've all experienced power outages. You may well remember major power outages like the Northeast power blackout of about a dozen years ago, where the whole Northeast lost power because a power line was carrying more current than someone had planned on. Because it was getting hotter from carrying the current, it expanded. Because it expanded, it drooped more, and it drooped enough to hit a branch on a tree, creating a short circuit, shorted out the power line. Now the next power line is carrying more current to make up for that. The same thing happens to that one, and all of a sudden you have this propagation of collapse through the entire network of power supplies. So these topics of probability events, group behavior, games in evolution, instability, nonlinearity, and network effects are key to understanding collapse processes. So we look at these different collapses from a number of different points of view, and it brings me to really the bottom line of my talk, and that is that the most important way to head off collapses or to manage collapses in the future, I mean, you may want some. You want to, we like the fact the Soviet Union collapsed. We like the fact that polio is collapsing. We try to get tumors to collapse. One way or another, the best way to manage collapses is to understand the dynamics behind them, how they occur. And I think that mathematical methods are one of the key tools for really structuring our analysis of those methods. And that's why I think mathematics has a lot to contribute to this field in concert with other disciplines. So thank you very much.